We looked at the fundamentals of computer vision. Okay. And then we looked at image classifications. In the day two, then we deep dived into object detection. We looked at the fundamental core concepts of object detection, and then what are the different model architectures for model detections. And we also looked at one of the important practical frameworks. Yes. um, yeah, this so there's like so what is object detection and how is it different from image classification? Anyone want to take a shot at it? Object detection is if I make videos from there, and if I want to detect the object, you see cost labels that object detection. Image classification is I detect the object, so I classify it like this cat or this dogs. That is image classification. Yeah. Okay. So image classification works at a very high level, whether we have to classify image into predefined categories, but it do not have the capability of localization. So the major difference between image classification and object detection is the localization capability, which means can I localize the objects that are present in this image? Image classification can tell there is a cat, but can it tell where exactly the cat is with the precise bounding box coordinates? It cannot do. Now, object detection, it can tell there is a cat and also give you the precise bounding box coordinates of it. Okay. Then we looked at some fundamental core concepts that are very important to understand at a low level to see how the object detection works. And one of the important terminology is intersection over union. Now, if we look at image classification, mostly what you required is to understand accuracy of the model. It is whether 90% accurate or 98% accurate. But then there are also different approaches to measure the accuracy of the model. One is to just take a ratio of the correct towards the total, but sometimes they are not well represented of the model's performance. So sometimes we use some advanced metrics like say F1 scores and precision and recall, but they are just the basic uh, model evaluation metrics. And for any accuracy calculations of a machine learning, deep learning model, the fundamental data unit of this formula is the number of true positives, false positives, and false negatives. And in image classification, it is very straightforward. If the predicted class matches with the ground truth class, it is a true positive. But in object detection, it is little more tricky. So you need to compare the bounding box also, because it is not only predicting the object classes, it is also predicting the bounding box, which is basically a numerical value. Now you need to compare this with the ground truth bounding box. For that only we use intersection over union. So it compares two bounding boxes, and if this overlap is more than a certain threshold, then we consider that prediction as a true positive, as a correct predictions. Then another important fundamental core concept is non-max suppression. Why non-max suppression is needed? Can anyone tell? Why it is needed and how it is implemented? Sometimes particle bounding works. Which one is the which one is A? So for one image, there will be multiple bounding boxes. We can do
be the final one, which is more accurate. So manually you can get the logic like how you calculation and all these things there. But this is an algorithm also.
Hmm. It was a very simple algorithm. You remember at top of your mind? Sorry? And that is the purpose of non-max suppression, like why we are doing it. So the purpose is to remove the duplicate bounding boxes because the model is trained in such a way that it proposes bounding boxes. It cannot tell precisely which just give one single bounding box. It just gives you all the probable bounding boxes. So that's why if you have 5 objects, it will give you like around 300 bounding boxes. But out of 300, you need to pick 5. So you need to remove all those unwanted things. That is the purpose. And I'm asking, yeah, so yeah, explain.
I knew it and that right.
Okay.
Then uh it's going to short like we first we short like maximum I will do words. So this one if we calculate 0.5, those are greater than 0.5 will keep them.
But before checking the IOU, what would be your first step to compare the mounting box and short them based on a certain numerical values?
Score would be
Hmm. So first step is to or short them by score and filter all the bounding boxes which are less than a certain scores. If it is a 50% for 0.5, or you can just straight away remove the bounding boxes which are 0.1, 0.2, 0.3 like that. So that, but that just a simple way, but um, anyway, if you understand. Then we looked at some key evaluation metrics. We looked at uh, uh, precision recall, and we also understand in detail how a precision recall is calculated for an object detection scenario, because the precision recall is a generic formula, and in order to calculate those true positives, false positives, and false negatives, we understood how they are determined in an object detection scenarios. Okay, so there, in order to determine a true positive, you need to compare two things. One is the if the predicted classes matches. Another is compare the IOU scores. Okay, only if the IOU is more than 50%, and then if the class also matches, then it is considered as true positive. Okay, and then we basically have a list of predictions. Okay, and then you have a list of ground truth. So what you do, when you are see all these things are already implemented for you, mostly you'll be using libraries. But if you want to implement it on your own, right, if you're writing code from scratch, then if you have the steps understanding, then you can implement it on your own in Python. So then you loop through all the predictions. You determine whether for each prediction, whether it is a true positive or a false positive. Then you loop through all your ground truth. And for every ground truth, whether do you have a actual correct predictions or not. If not, you classify them as a false negative. And in predictions, you either classify them as a true positive or false positives. Then finally, you have a list of true positives, list of false positives, and list of false negatives. Then with that, you can easily calculate precision and recall. Okay. Now, what is MAP? MAP is basically that you calculate this precision recall for different thresholds. Okay, then you will get a precision recall curve. The area under the precision recall curve is nothing but your mean average precision. It's not exactly that. It's a little more detailed than what, but a simple high level understanding is you can just imagine like that. Okay. See, this one, I think we might not have touched in detail the last week because we went into a more practical discussions than this sort of a high level theoretical discussions. See, this is good to understand as the historical evolution of the object detection models. Probably last 10, 15 years after the deep learning era started in 2012, first few years, mostly it was an image classification model. There are a lot of legacy historical models, like starting from AlexNet to InceptionNet, then VGG, all those models, which probably in this today's fast evolving scenario is probably a little bit obsolete to learn all these old models. So that's why we skipped it. But still, in terms of practicality, uh, the most widely used models would be the ResNet. And all of these models are based on convolutional neural network models. Um, but then in around 2020, I think in COVID period, uh, there was a new class of computer vision models start evolving, which is transformer based computer vision models, which we will touch upon today. Okay. And then that is like image classification, historical evolution. But if you see the object detection's historical evolutions, initially, they were starting with sort of a brute force approach where you have an image classification model and then you have this big image and then they break down this image into multiple windows. And for every window, you can run image classification model. And then finally, you can try to locate the object, right? With that windowing technique, sliding window technique also, you can try to find the location of the object, but that is very, very inefficient. It is like a lot of, it takes a lot of time. It might take 5 minutes to process like one image. Then researchers came with more efficient techniques. First generation models of those efficient techniques is all RCNN based models. So they call it RCNN families. Um, they are, if you look the object detection at a high level, if you go into look into the literatures, books, will tell you that the object detections comes under two main categories. One is a two-stage model, another is a single-stage model. Okay. Two-stage model is all those RCNN family models. So it starts with RCNN, then came faster RCNN because RCNN itself was taking couple of minutes. Then making the object detection to process under a minute was a great achievement like 10 years back. Okay. Then came the faster RCN, and then that evolved into another model called mask RCNN, which we will look into it today. But during, I think, 2018 or something, there was an famous computer vision scientist called Joseph Redman. Okay. Um, he was a researchers in probably one of the universities, or I'm not sure. So he came up with a model that, hey, why it has to do it at a two-step? Can we not do all this in one single pass? Okay, so he came up with the concept of YOLO. YOLO stands for you only look once. Okay, before that, you first pass one image, get the region proposals, then you process these region proposals to identify the objects present in an image. It was always a two-step process. Then Joseph Redman invented this technique called YOLO, you only look once. From there onwards, it was a breakthrough moment for object detection. Okay, mainly because of the computational efficiency, and because of that, it was like 4x, probably 10x faster than the previous faster RCN models. Okay, and because of that, you could run YOLO in real time. Actually, if Joseph Redman did not came up with this concept, none of your vehicle traffic monitoring, none of your industrial quality inspection monitoring would have been possible, because for that it takes couple of minutes. Now I want to monitor my traffic in real time, but for every image it takes couple of minutes. It doesn't make sense practically for me to use these AI models in real world applications, right? So he came up with this concept so that we could efficiently run these models in low compute environments in real time. Okay. So that's why it's considered as a breakthrough moment. But at that time, when he released the first YOLO model, the YOLO model compared to the faster RCNN, the accuracy was comparatively lower. Although he achieved a breakthrough in the speed, the accuracy was comparatively and significantly lower than fast RCN. Then it evolved. So now starting from YOLO V1, we are now in YOLO 26. So it's probably have gone through some 10, 15 revisions. And now we have almost the same accuracy as Foster or CNN, or even better for accuracy than of two-stage models. But at this time, it is even more faster. So that's the evolution it has gone through. But we do not have the time and bandwidth to go through each and every model. Probably that is one of the exercises for you. If you're really interested and passionate, you can go and read these papers, at least couple of them, to understand how this model has been evolved, right? Sorry? Yeah. So if you take an image, the model doesn't know what is the probable regions where these objects are located at. So for that, we have one model which just does this scanning, and then it just gives you a very coarse region, ROI, region of interest. So it just draws some sub windows of the image, and that region is then fed into another model in order to refine and identify the exact bounding box coordinates of the object. So it is a two-step. First, you pass the image, get the regions where the object would probably be located there. Then you have another model which take this region as an input, refine them, and then give you exact the bounding box coordinates of. Okay, so that's basically the object detection. So next week also we will see how object detection is even more advanced. And recently there are a lot of work in applying uh, how do we call this LLM concepts or the multimodal LLMs for object detection. Okay. See, last week we did some quick fun exercise where we gave this image to ChatGPT, Claude, and Gemini, and Claude did not give a proper object detection coordinates. It struggled. And one of you tried ChatGPT and it gave you a good boutique box coordinates. But if you understand carefully, probably ChatGPT uses an object detection model YOLO underneath to get this. So it's like sort of an agentic thing, that okay, this guy is asking for a bounding box coordinates. It used YOLO as one of the tools. Okay, so then he passed this image into YOLO, get the bounding boxes, gave it to you. So it's like using YOLO as a tool, one of the tools. But now recently, last week, there has been some advancements in this using the VLMs directly for object detection. That we will see it in the next week. So there are some interesting advancements. Probably I also have to update myself. Almost it's like every week something these new things coming, but we don't want to go behind everything. But if there is some really relevant, important things comes, I think we should discuss that. Probably next week we will discuss a couple of approaches on how do we apply these large language models. Rather, a more relevant term would be is a visual language models, VLMs, for object detection. Okay. All right. Oh yeah. Good. Yeah, yeah. So that's what I was going to switch gears today. All right. So we move from object detection to image segmentations. So today we will see what is image segmentations, how it is implemented. We look at different model architectures. First, we'll see with some legacy approaches like mask CNN and UNet, which it is not totally out of relevancy. You would still be needing such models to train on your custom data set and build some AI applications on top of it, be it a medical diagnosis or industrial inspections or vehicle monitoring or surveillance monitoring. You would still need such models. Okay, it's not totally uh, out of the game. Then we will look at a new class of models called vision transformers. And then we will also see one of a very interesting model that came out recently from Meta, that is segment anything model, which is also sort of we are touching on the generative AI area of the computer vision through the segment anything model. Okay. This is also something similar to LLMs, like you can like prompt these models and get outputs. Okay. It's very interesting. Have anyone heard of these models before or used it or just gave a try on their demo site? No? Okay. Basically, it's a segment. It could get your segmentations by just drawing a bounding box around it or just clicking the objects or just do a full scan and then it give you all the segmentations automatically. It's a very powerful. So what would be a learning path for segmentation is understand what is mask, because this is the term that will be repeatedly used in segmentation. Um, so what are the class labels? What is the object identities? And how do we use segmentations for a full scene understanding? So there is also a classical view on segmentations. So before all these machine learning, deep learning era started, people were still doing segmentations. It is also called as thresholding. Right? So segmentations is generating mask, and then you could also do mask thresholding. Then came the deep learning workforces like the fully connected network, UNet, mask RCN, and how they changed the segmentation landscape. Then came the transformer era where slowly all of the computer vision deep learning neural networks were moving away from the CNN to transformers. And then came the foundation model eras, which basically inspired from the LLMs and SAM was the one of the breakthrough models for the foundational vision models. Then we'll see at some practical training and deployment tips, how to curate the data, what losses to be used, How do we appropriately evaluate a segmentation model? What are the different failure scenarios and how do we diagnose them mathematically? And what are the correction trade-offs for these segmentation models? Because again, these segmentation models are almost 2 times, 3 times compute heavy than object detection models. Okay. Now, object detection models can also give almost the same that segmentation models can give, which basically can draw a bounding box around it. But the segmentation models give you the precise mask of it. So then your compute also becomes a sort of a trade-off between whether you need a precise boundary or you are good with your high-level coarse bounding box. So if you look or ask yourself what is image segmentation, you could answer them in just one line as shown here. Image segmentation is basically a problem of classifying each pixel in an image belonging to a certain class. Do you understand this and follow this? Right. So images are nothing but a matrix of pixels. It can have, if an image dimensions is about 1,000 by 1,000, so it has about 1 million pixels. Right? Then image classification is basically classifying this entire image as like one data unit and telling them what category of the classes this images belong. But imagine that if you break the images into pixel level data unit and then classify each pixel instead of classifying at the image level, then that is what an image segmentation is about. And that's what the modern deep learning image segmentation model does. Now, you could classify the pixel into either two categories or more than two categories. If it is just two categories, then it would be a binary classification. So then each pixel of an image is either a black or a white. Okay. Then that also is nothing but a thresholding of an image. Right. Thresholding is just converting an image into a black and white image, binarization of an image. And that's also called as thresholding, and that is also image segmentation if it is just two class. But image segmentation is not just limited to two class. It can do more than two classes. Now there are three main types of image segmentations. One is as semantic image segmentations, another is an instance image segmentation, and another is a panoptic. Now here is an classic example of what these three types of image segmentation means. On the left hand side is an input image. This is an outdoor scene, a traffic scene where there are a lot of cars, buildings, pedestrians. You also see some backgrounds like skies and trees, roads, and etc. Now, as I explained this image through my natural language, right, I describe the scene into different categories. Right? I say there are a bunch of cars, there's buildings, there is pedestrians, there's a sky, there's a tree, road, etc. This is nothing but semantic, right? That's what how we communicate using our natural language. So we group them semantically. That's basically what the semantic segmentation also does. So it segments the image into semantic groups. So in this, all the cars belongs to one semantic groups. All the pedestrians belongs to one semantic group. All the buildings belongs to one semantic group. All the trees belongs to one semantic group. The background sky belongs to one semantic group. The traffic lights then belongs to one semantic group, and the road belongs to one semantic group. So this is called semantic segmentations. Now, probably when it depends on your use case, probably this is not very useful if you're trying to do a self-driving car or a vehicle monitoring system, right? So in this, there are four cars, but from this mask, I wouldn't be able to tell there are four cars. I would be able to only tell there is like one separate car region here and another one car region here. But I'm not entirely sure there is multiple cars in this big car region, but I wouldn't be able to tell how many cars. Probably there is two. I can make a wild guess, but actually there might be three or maybe four. It doesn't give you a precise separation. So that is where the instant segmentations comes into the picture. And the instant segmentation is a more relevant concept in most of the practical segmentation use cases, such as your vehicle monitoring systems, your self-driving cars, or your industrial inspections. You just not only need to separate them semantically, but you also need to segment them instance wise. Each vehicle has to be separated, each pedestrian has to be separated, each product on my quality automation system in my conveyor belt has to be separated. Okay. Yeah, probably they use panoptic, which I'm not that sure. Um, so this is, I told you that, we need the separation of the class, but I also need, see, in this, I only get the car and the pedestrians, but I was not able to get where there are the buildings, where are the skies, or where are the roads and everything. Now, can I do instant segmentation on a road? No, because that is a continuous space. Car is a more of a discrete space. I can tell one car, two car, three cars. But can I tell one road, this two road? There are four roads in this, but you won't tell, right? You will tell there is just a road. Yeah. It's just a continuous space. And for sky, you're gonna tell there is two sky. There's just one sky, right? So then that is where the semantic thing comes. So if you combine the best of both semantic and instance, that is where the panoptic segmentation comes. So you get the instance segmentations of all the objects where your discrete counting this makes sense or possible. And then it also gives you the semantic segmentation where this discrete counting is not relevant or possible. So self-driving cars is basically might use this, and this is good best for full scene understanding because self-driving cars needs a complete understanding of the 360-degree. In yeah, that yeah, yeah. Uh, So that you could get it from object detection also, right? So this one is more of a next level of granular localization. There is no any purpose to separate the building as long as it just tells the building is like one. I'm just good with it. Yeah. What would why would I need to tell one building, two building, three building? Like I just need a total semantic grouping of just saying the building. For car, it is useful for me to count the cars. For pedestrian also, I can count the pedestrians, which probably can use for my signal predictions. It can tell you the density of the pedestrians. If there are like 1,000 pedestrians, or it may not 1,000 possible. Let's say 100 pedestrians are waiting at pedestrian crossing. I will immediately open the pedestrian crossing, right? So like those kind of applications I can use. But what is the purpose of counting the buildings? And if you really have a purpose of counting, probably aerial survey, right? Like remote sensing. There you need to probably count all the individual trees separately. So if you go to sort of Finland, for them, the major industry is forest. Okay. So they probably have an satellite imagery and they need to count up the trees, right? Probably for them, they might have separated each tree separately like that. It depends on the purpose actually. Yes. If your use case demands that, hey, I need to separate buildings separately, then you could train instant segmentation models on those separating each building as a separate mask and count them. But then you should also label them accordingly. So labeling effort also will increase. It's also a trade-off. You shouldn't be separating the buildings for just for the sake of separating them. If it is really needed, then you go and build a model to separate the buildings. But you should also estimate what is your project efforts, and you need to put efforts in labeling all those separating the buildings. Mostly we use instance only. Yeah. So even if you take medical diagnosis, you will have an image and you will have some these cells, right? And these cells can be individually annotated, and the instant segmentation can be trained on them onto separate these each individual cells. So sometimes these individual cells can be a little bit closer. But if you segment them as a two separate objects, it will give you two cells. Okay. And then in medical, it is important that you separate these two cells and measure these cells separately. Because a precise measurement of these cells will indicate a certain diagnosis, right? Whether it is a cancer cell or I don't know, I'm just making up something. If it is within a limit, they will say, hey, you're okay, you can just go like that. But if it goes beyond the limit, they may treat it just with some tablets or something. But if it goes beyond a certain size, then they need to sort of advise you for surgery. It could help in some stones, right? In gallbladder stones or some kidney stones. If it's they also measure the size of the stones and they say that hey, if it is just small, it's just coming out, it's very within the limit, you just take tablets with it. But if the size of those stones are a little more than the limit, then they say hey, this cannot be treated with tablets. You need to go for surgery. Those kind of critical decisions can be made. One separate model to Mhm. Yeah, should be possible, but it's going to be really challenging. I mean, identifying a brand of a car could be challenging, but you could. I'm just telling you. I know you're giving some imaginary example, but I'm also telling you that you could separate a car type, hatchback from sedan, a sedan from an SUV, from SUV from a van or something like that. But can you separate from a Maruti Swift from a Hyundai i30? It could, but it's going to be a little more challenging. Yes, this will be much, much slower. Yeah, so the object detection just draws a bounding box around it as shown here. Okay. And if you see the segmentation, it draws the precise boundary of the shape of the car. Okay. From the shape of the car, you could tell whether it is a Maruti Swift or a Hyundai i20. Those kind of things can be done. And you could draw a bounding box from the mask. No, no. Mm. Hmm. Yeah, you're correct. Maybe if you're just looking at the back of it or front of it, probably you need a side view. At least if you have three views or a isometric view, yeah, something like that, then it is possible. No, no, yeah. You have to define the problem. So there is two things you need to take care. Based on your use case or the problem statement, you have to select which of these segmentation approach you want to train. Okay. Then if you say that, hey, I need an instant segmentation model for my use case or problem statement, then you go and find an instant segmentation model. Okay. What are all the different models which are there for instant segmentation? That is one thing. Second, you need to curate your data, and then you need to label the data in an instant segmentation way. Okay. Okay. So this Claude Opus, Claude File, so they are like that powerful to. There are some LinkedIn posts and some. I don't know exactly. Yeah, they are very powerful. Like um, as I told you, right, recently I was trying with this interior 3D renders. What this interior 3D rendering thing could take weeks. I just did it in like probably they got like a little bit sort of taken back. What they could do it in like 2 weeks, 3 weeks, and doing it layer by layer. This ChatGPT is doing in like minutes. And then you don't need those sort of skill set also. All you need is to just to describe it properly in your language. And if you're articulate enough, then it gives you an excellent result even though 3D rendering you can not able to do it. Mhm. How they process that they can create a everything further they the okay, so that what how they call it? They put a camera in their head and then they do. Yeah. It's called egocentric views. So when this Meta came with this classes, I think 5 years, they were trying to build something called Omniverse or something, right? And then they were collecting egocentric data, which means they sent these camera kits to all the chefs, and they will record all those cooking videos and all those things, and they use that video to train the robot. And yes, I think the Meta's aim was not to build a robot, but that is their moonshot. But on a midterm, they are building this augmented reality, because augmented reality also needs your environmental inputs. So those AR glass from Apple, Google, Meta's this one VFXs, all those this model. They also run models on that. Yep. Yep. Yeah, that is basically Meta. Yeah, that's basically also have some privacy debates going on. It's a little bit scary. Yeah, there's also needs a lot of need for AI regulations and laws which governs all these things. Yeah. Okay. Okay, let's bring this problem into input output mapping. So I always look these machine learning as an input output mapping. That's all they do. Earlier, we need physicists, we need mathematicians, we need chemists. Nowadays, all you need is data, and then just give those data input to a model and tell what the expected outcome. Then the model learns these mappings. All it is doing is learning the mapping from input to output. So in image segmentation, what is the input? It's nothing but an image. It could also be a video. It could also be a 3D image. It could also be sort of an LiDAR data or whatever, right? But I'm just for simplicity's sake, I have taken this an image. And basically, this model is expected to output a finite subset of possible binary mask of all the connected pixels in an image. Now, this binary mask, based on the number of classes, it could uh, it basically depends on the number of classes. So in this case, it will just output like two binary mask, one for an uh, car, another for a pedestrian. And within that binary mask for car, they can have some identifier to tell this is car one, this is car two, this is car three, and this is car four. So they will give some sort of an connected pixels identifier. Understand? Um, in this case, the binary mask is more simple to understand. It just gives you a blue, red, a green, gray, blue, purple, or pink, yellow, or black. Okay. So probably let's say 6, 7 mask is what it will output. Okay. Each binary mask is nothing but a black and white image out. If you take a binary mask of car, wherever there is a blue region, it will be white. Remaining all region will be black. If you take the binary mask of the pedestrians, wherever there is red, it will be white. Remaining all regions, it will be black. If you take the binary mask of purple, it will be white only in the road region. Remaining all will be black. So like that kind of black and white image, which is nothing but otherwise called as binary mask, okay, there will be like 6, 7, each one for each class. Okay. That's what the model is expected to output. It expects to output finite number of possible binary masks, which is nothing but the connected pixels in an image. Yeah, yeah, yes. And then I need to combine. We combine all the binary mask, then you'll get one single black and white where all this blue, red, purple, blue, everything is white. Probably it will be like all white, right? Because every single pixel is either black and white. So that's why they keep it separate. Yes. So on a typical Intel hardware, um, an object detection like YOLO takes, let's say, about 200 to 300 milliseconds. The segmentation model can take about 1 second or so. If you are able to do it within 1 to 2 seconds, that is incredible. But nowadays, there are a lot of models that can do in sub-second latency. It is not possible to do it in sub milliseconds, but it is possible to do it in sub-seconds. And particularly, that is, I'm telling it in CPU inference. But if you're running it on a GPU in cloud, or if you have NVIDIA GPUs installed in your hardwares, then you can do a more speed with those kind of GPU accelerations. So the problem comes is when you don't have access to those GPU accelerations. So that's why you need to design your pipeline in such a way that it is deployable to a CPU kind of environment. But training, it is not possible to train on a CPU. If it is just few images, you could do, but few 100,000 images, I mean, it might take months to train on CPU. So just be careful on that. So why I say this, do not give overhype to your managers or someone say that, hey, I'm going to train the model in like CPU without understanding what hardware requirements you need, right? So because the hardware is a bit expensive, then if you're just proposing a project, you also need to take into account the investment that is needed for all these training costs, the inference cost. Okay. So when you are moving towards some more of an AI scientist or an AI engineer kind of role, all these 360-degree views, practical consideration is also important, and that also makes you stand out that you are not just a typical training evaluation kind of guy that anybody can do. You can just open some Google Colab, load a data, just train it and show them peer curve. People thought that was data scientists, but think that's why 80% of the project failed. So you need to know what is your hardware, how do we deploy this, how do we put into the hands of the users. Okay, there's a lot of engineering is important. Okay. Mm. So let's also have a classical view of what this image segmentation is about. Before this deep learning thing came, people were still doing image segmentation, right? With all those classical computer vision slash image processing technique, which we touched upon in the first day one. The most important one is the thresholding, just to tell, okay, if the pixel value is more than a certain value, just make it white. Otherwise, just make it black. Okay. Uh, if your image is naturally thresholdable, right? If you have a very clear differentiation between your foreground object and your background object, doing thresholding is pretty straightforward. But there are some other advanced techniques also, like also thresholding, adaptive thresholding, all those things. Then there is also you can apply clustering, which means you could take some k-means clustering, and you can just imagine all these pixel intensity values or color values, and then you can just imagine that as a sort of a three-dimensional space clustering, k-means clustering. And if you tell them that, hey, can you cluster these pixels into two groups or three groups, probably it can do a certain level of segmentation also. Then there are other things called region growing. So I'm not sure, since most of you or all of you doesn't have a computer vision or image processing. When we were doing this classical computer vision, we used to use some techniques called watershed image segmentation. Um, that they are nothing but some region growing techniques, which means that they start with a sort of a small area, and then they grow this region. It, it's like if you have a dam, right, and you have a big pool of water, and then you start in the center of those dam, and then you start growing until you hit the rim of the dam. Okay. After that, you cannot grow because there is a border. There is also there is a big wall around it. That is, we can identify that mathematically. Then we stop there. So then we have one region, and remaining all region is another uh, area. Okay. That is basically a region growing. We also, very popular method for segmentation is edge based. So basically, canny edge detector, swabble edge detector, and there are some other advanced edge detection models, which gives you the a sharp gradient change in your image intensities, and those gradient changes are identified, and they are then grouped into one area, and that also gives you a image detection. Okay, so all these above are all classical techniques, and then came the deep learning area, right, which basically made all those old techniques little bit relevant. But see, again, not everywhere you could use deep learning. Okay. I have a lot of scenarios where I was reached out in my company that they will just give you two images and then tell you that, hey, can you segment these objects from this image? Okay. And then I build need to build a quick POC and then give them a answer that whether this is possible or not. Okay. Now, at that time, you could just use all these classical techniques, tell them, hey, it's possible. Um, but what we also recommend is to go with the deep learning approach where we would need a lot of images. But they will say, hey, we don't have images. All we have is just 10 images. Can you build a solution and deploy that into my pipeline? That's all they will. So that's where all your classic computer vision techniques will. I mean, I'm just giving you a sort of an advice. If you're really seriously passionate about into this area, these are the some techniques that you might want to learn. So don't worry, you just go and use your Claude Code or Copilot. Or, but what I'm saying is, all those tools are there for you to now do all the heavy lifting for you. But you don't know, right? You know those terms, you know the basic understanding. If somebody reaches out to you, let's say your senior leader is reaching out to you and say, hey, my customer gave me these three images. We just want to quickly validate or investigate so that we can come up with some solutions for them. Okay. Now you're gonna send back your senior leader, hey, go and collect 1,000 images and come back. Right. So then I need to approve my this also. So I will just build some quick solution and then I will tell him, hey, this is what is. This is where we could reach with this image, and this is the limitations. If possible, we should go with this approach and collect more images. And that builds a little bit more credibility for you, right? It's a more solution approach than just saying, yeah. You start with this classical computer vision techniques like thresholding, do some simple thresholding like odd shoe thresholding. Edge detection is what most people do, edge based things. Those two techniques, thresholding and edge detection. Right. Trusting sometimes works, but yeah. Yeah. See, if you have gems, right? You have this color gems, right? Cadbury gems. Yeah, that's it, right. You might use it as a sort of a pet project just to show that hey, I also know all this concepts. In real world, it's very difficult. No, I did not annotate it. It's I had this, and I can give this image. So you can go and try all these techniques. Okay, just put it into Copilot or Gemini in Colab. Just ask them to, hey, can you write a thresholding? Otherwise, go and read the OpenCV documentations yourself. They all gave code examples. You can, huh? Yeah, if you go to see, yeah, OpenCV on they have a proper documentations. Then you can. They also have some code examples, API documentation system. That's why we used to do long back, but nowadays everything is fast paced. So now you go and prompt. Yeah. Yeah, that is a major risk. This risk and this view was there for all the cloud service providers, right? So if you go to Saudi, they don't have any AWS, any GCP, any Microsoft Azure. They just have their own private cloud. So very sensitive regions like Saudi Arabia or probably China also, right? I don't think they might have their own cloud provider. They have their own Google engines. So similarly, the same thing happened for AI models also. If you're more tied up towards certain service providers like OpenAI, in future you might also have some risk. I recently we also see that like they rolled out this Copilot, GitHub Copilot, and everyone was using left and right. And a couple of weeks back, I think they changed the usage limits, I think, right? And nowadays we are getting a lot of complaints. We ran out of limits. Um, so then they're still figuring out that, and they're asking people go back to your old, write your own code. But it's yeah. Yeah. So this is what I think Anand Mahendra asked Sam Altman when he came to this. Hey, how can we build India LLM? He said, forget about it. It's hopeless. He told. Right. So you can take that challenge, but maybe SLMs, those kind of models. But still, people are building India homegrown LLMs like some companies like Sarvan, Bharat Clear. But yeah, can they outperform OpenAI or Cloud? I don't think so, but at least some serious efforts are good. Sorry? Ah, okay. Yeah. Yeah. Yes, yes. I think not everyone are using API calls. There are also companies and teams who are training their own models. Yeah. Yes, yes, yes. Yeah, there was also one very talented person was there in AI 07. Bernard Paul is actually from Army. Uh, so he also developed a very impactful AI models for this security modeling, border security. Right. Yeah. Sorry? Okay, okay. Hmm. Hmm. Yeah, yeah. China is good. Israel is very good. So I don't know if you have heard about that one company called the Mobile Eye. That was what was powering Tesla's Copilot, this one, autopilot. So Tesla has this autopilot, right, where you can just activate it and it just it takes the full control. Yeah. So it has sort of level 3 or something. All it needs is it's just checks whether there is a human. You need to just put your hands on the steering wheel, but it just does all the steering and everything. So, but so they were actually using 3-4 years back. They were still using Israel's mobile eye technology. So then they exited. They got separated. Then Tesla they built their own system. Oh, there's a very good video by Andre Karpathy on 2021. He gave like almost a very detailed view of their ADAS system. Can just read that, share that video after that also. So this guy is one of the top minds. I think you might have heard about him, right? Was there in Tesla? Yeah, no, he quit Tesla and he was working on something else for a couple of years and now finally he decided to join. This is the one. So they in this he gave a very detailed insight into how this AI these games pretty advanced. So they use something called HydraNet. Uh, so they take video streams from the 8 cameras, and then they fed that into this model, and then they have to basically combine all the predictions into just once. I kind of don't remember that, or I need to watch this video again. But that's a high level. But it's not about the model. There's significant amount of the time he spent in this video explaining the data labeling. So Tesla has an army of data labelers. So whatever the model you built, you cannot do without data. So they had a sort of a model to label them, then someone to review those labels, and there is also synthetic data generations. Because you cannot create an accident scenario. You cannot collect data of an actual accident, right? So they need to create or synthetically create that scenarios and expect that the synthetic data is actually a realistic representation. Then it will work in actual scenarios. But uh, that's why if you see these Teslas and Waymos, they are not rolled out even 100% within USA itself. It is just rolled out in very selected cities, which means probably I'm just guessing that it is just trained on only California data. And if you go to New York, it might not work. I mean, if you are not able to work within your country itself, how it will work in other countries, right? India, I don't think it will work, but still people are attempting it. They are very bold and dare to attempt it. Probably it's like a very POC level. They get some funding and after 3 years they exit. It's so down. Okay, so I think that's a lot of chat. This already we saw. Okay, so last time we saw some very fundamental core concepts of object detection as intersection over union, and then there is like non-max suppression. Then we saw what is precision recall for object detection. For image segmentation, one of the main metric which also can be used as a loss function is called dice loss. Okay, It's also sometimes called as Jacobian matrix, if I'm not wrong. Okay, so basically it says that okay, now you have a ground truth mask, okay, and then you have your predicted mask. Now, what they call this dice coefficient is that take the sum of the predicted and the ground truth mask. Okay, then you basically take the intersection of the predicted mask and the ground truth mask, and then you take the ratio of that. Now, there is that basically tells you like how good the predicted mask is. Okay, so which means if your dice coefficient is 1, which means a very perfectly overlapped mask. It's similar to bounding box only. But instead of just taking the XY coordinates, okay, in this they just take the count of pixels. Okay. Then if your dice coefficient is 1, which means it is a very perfectly predicted mask. If your dice coefficient is 0, which means those masks are totally separated from each other. Now, from the dice coefficient, you could calculate the dice loss by just separating it from 1. Okay. And then this dice loss is used in your model training. It's a very similar to intersection overlapping. Then we also have let's touch upon the loss functions used. Um, so you all know the Gauss entropy loss. It is used in image classifications. It's used in object detection also. So object detection also, if you compare the loss function with the image classification, it is a multi-task loss because in image classification, there is only one single task, which is to classify the image into one of those three different categories. But if you see the object detection, it is a multitask training, which means it has to do a bounding box predictions and it also has to do object classification. So there is two tasks there. Now, tell me out of these two tasks, which one is a classification and which one is a regression? You follow me, right? Okay, so you understand that the object detection is a multitask problem because it does two tasks parallelly at the same time. That is one to predict the bounding box of the object, and the two to classify this object into one of the predefined categories. Okay. What type of problem is these two tasks? So machine learning also has a high level problem types. The two major problem types are within that classification and regression. So classification is for categorical problems. Regression is for numerical prediction problems. Understand? Now, if you come to object detection, you have a multitask. One is to predict the bounding box. Another is to predict the object classes. Okay. So you have one regression problem, one classification problem. Now in your machine learning for your classification, what laws you will use? For your regression, what loss you will use? Okay. Yeah, that's what we use. The same approach would be here also. So when you're training an object detection model, you will use two laws. One, cross entropy loss, since it is a multi-class classification. They will use cross entropy loss for your classification. Another, they will use a regression loss like um yeah, but we cannot apply mean square error for bounding box prediction. So then what you will use? You will use IOU as a loss. Right? So IOU also gives you a numerical value between 0 to 1. So 1 means no loss. 0 means it's a So basically you calculate IOU and subtract it from 1. That basically becomes your IOU loss. Right? So you should understand also at the intuitive level, high level, what would be the right loss function I should select for my deep learning models, right? So for object detection, you have this IOU loss or see and cross entropy loss. Similarly, for segmentation, you can also use cross entropy loss together combined with dice loss to train your image segmentation model, right? So there are some advanced loss functions such as weighted loss or focal loss. Okay. This weighted or focal loss is also used in your image classification also because they are the advancements that was made in different years, right? So they started with cross entropy loss, and then they found that see among if you're having 1,000 image, okay, not all of the 1,000 images is of equal importance. Okay. Some of them are more important to train your model and tweak your model than the other features. And how do we identify those important ones? The harder the image, the more the important it is to train your model, right? Which means that if your model is making mistakes in first few epochs, those images will get more traits in the next few iterations. That's why they call it as Pokeballs. So they will give a certain weights based on the mistakes that it makes. So the next time it will focus on those mistakes, right? Okay, because just training it on the easier examples and again doesn't help the model to learn, right? So we also, when we are preparing for exam, you might focus more time on harder chapters than the easier ones, right? If I have like 12th grade physics, probably if I remember vaguely, probably I think the second chapter was the nightmare for me. I can still remember. So we spent. I just open and start with the chapter 2, and then go, and then probably for me chapter 8 was more hardest. So first for me I was peaceful if I finish all these hard chapters, and then I focus on, and then if I have whatever the rest of the time I would just go fast in the. That's how we would plan our time because we have a very limited time. So likewise, you could also imagine that model. Okay. Yes. Yeah, that's a similar. So, okay, I think we can take a break.